begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Hello everyone and welcome to the webinar. My name is Bob Wentz and I shall be the moderator for today's webinar. The webinar is entitled A Digital Approach to Insight-Driven Network Stability, and it will be presented by Alan Jeffrey, Anna Boyles and Chris Hinton of Thames Water. There will be a short time for questions and answers at the end of the presentation, but please note that the presenter's details will be shown during the Q&A session should you wish to contact them for further information. Please also note that during the webinar, you can post your questions using the Q&A button in Teams. At the end of the webinar, I will put up a slide showing details of the following webinars after this session. So thanks very much, and I would now like to hand over to Anna.
Thank you very much, Bob. And thank you very much for inviting us to speak and give us the opportunity to speak at this conference this morning. So, digital approach to insight-driven network stability. Little bit of a background in terms of the team. So my name's Anna Boyles. I'm head of performance risk and optimization within Thames Water, and I sit on the wastewater networks lead team within Thames Water. When we refer to wastewater network, that is very much including our pumping station asset base as well. And the remit of the team is a delivery function around planned sewer cleaning, around sewer depth monitoring installations. We do a whole range around network protection, education around fog, environmental protection with surface water outfall, misconnection investigations, and so on. But what underpins our activity within the team and wider, the special source, if you like, is the work that the data insight teams, the above and below ground data insight teams led by Chris and Alan, who you'll be hearing from shortly. And that's really the area that we're going to focus on this morning. So the background, why are we doing what we're doing? So AMP7, for all the industry, for every water company, we've got more and more challenging targets on many fronts, including the performance commitments to our regulators, to the commitments we make to protecting and enhancing the environment, and to our customers, as well, of course, operating costs. They don't go anywhere. Our assets and our estate generally are aging. Our operational resource is static, and all of these present really big challenges. Network stability is a key enabler to allow us to be far more considered and planned in how we deliver our service to achieve some of the metrics that we need to. The more our business is in a stable state, the more planned activity we can do, and the less reactive we can do, the better. So core challenges as well, the world has changed in the last 12 months. The COVID impact has hit the country, the world, very, very hard, but that has had a knock-on effect to our industry. The way I would describe it is, I think the industry responded really well. We won the war, if you like, but now we have to win the peace. Coupled with climate change, coupled with growth, population growth, all of those really big national and international challenges that we've got really do play a factor. On top of that, as I mentioned, we've got operating expense, we've got resource performance, the risk is only ever increasing with an aging asset base, the complexity around our compliance, and you put all that together, the probability of failure is going up. I came to Thames Water probably around 7 years ago. I've been in the industry my entire career, and as well as the kind of scale and size of the physical asset base that we deal with, if you translate that into data, it's quite staggering, the kind of put some of the numbers up on the screen to kind of give you an idea of what we're dealing with. So like I said, when we're talking about above ground, we mean pumping stations in this context, and below ground is our wastewater network. On above ground, we go through 2 million SCADA transactions a week. We've got over 5,000 pumping station locations, which incorporate 9,500 plus pumps. We've got 15 million customers across our waste and clean asset base. 2,500 SAT work orders a week. These are big figures. You translate that into the below ground waste network, you know, we're looking after not far off 110,000 kilometers of aging sewers. We've got 2.5 million manholes there or thereabouts. In terms of weekly, we deal with around 1,400 blockages a week. We deal with 5,500 customer calls on average, and those calls inevitably turn into investigation jobs, and we go through around 3,500 investigation jobs a week that range from really serious pollution, flooding incidents through to your kind of more standard blockage incidents through to other investigations. There's some really big figures in there, and the kind of phrase that is commonly used is data rich, knowledge poor. So how did we go about approaching that? Well, the key bit was to really gain data insight, but in a measured way. How could it be used on a practical level from an operational improvement point of view on a daily, weekly, monthly, annual basis, as well as the longer term tactical interventions and even strategic interventions from an AMP on AMP planning perspective? That was kind of really what we aspired to do. How did we go about doing this? So the tool that we use is called Icubed, off the information, insight and intervention kind of ethos that we've got. And it is really important to stress that when we talk about Icubed, it is an ethos. This is not a piece of software. We do use lots of different pieces of software: Azure, SQL, Server, Esri, so on and so forth. All the applications that many colleagues in the industry use, but the difference here is that we take that information from all of these data sources, and we really gain the insight. We really understand what it's telling us, and that kind of quite grand statement on the screen around democratization and husbandry of data is a key enabler. Well, in practical terms, it means everyone at any area of the business should be able to utilize this data, should be able to have one version of the truth, should be able to make interventions, whether it's something small or whether it's multi-million pounds worth of investment off the back of it. So in terms of you break that down even further, what have we included in this Icubed ethos? What have we kind of prioritized at looking at the themes? Well, the kind of Venn diagram that you've got in front of you now covers all of that. Is risk, resilience and efficiency equals that Icubed ethos. It's important to kind of get your front end data right going in there, but equally the outputs of it around benefit tracking, around intervention tracking. What are we actually doing and what are the benefits of this? All of that was really important to us. So that's given, I hope, a quite a high level understanding of what problem we are trying to solve. And I'll hand over now to to Chris, who will talk in more detail around the below ground wastewater network part of Icubed, and then we'll move on to the above ground with Alan. Over to you, Chris.
Thanks, Anna. Good morning, everyone. My name is Chris Hinton and I'm the Asset Performance Insight Manager at Thames Water. I'm going to introduce you to the Icubed below ground model that we've developed. Next slide, please, Anna. So the Thames Water operating area covers a wide area from London in the east to towns like Luton, Oxford and Swindon in the Thames Valley, and we maintain 109,000 kilometres of sewers across this operating area. As part of our drive to increase the volume and improve the efficiency of our maintenance of the network, we've developed the below ground Icubed risk model, which is a data-led sewer risk prioritisation model built in geographical information systems on the Esri ArcGIS platform. GIS data from the company's corporate asset register has been combined with incident data such as sewer blockages, sewer flooding and pollutions, work management data like sewer cleaning and sewer repairs, and then localized risk factors like watercourses and local nature reserves to build an overall asset level risk prioritization model. Standardized risk scorings used in the model to prioritize all sewers against each other, with additional asset and area characteristics used to assign relevant intervention types to different sewer failure modes. Our planned programme of works is then built up from this asset level view of risk into large programmes of sewer cleaning, CCTV survey inspections, customer education of residential properties, network protection, which is visiting restaurants to engage about effective grease management and disposal, sewer depth monitor installations, and then sewer rehabilitation. Next slide, please, Anna. Our planned sewer cleaning programme comes from two main sources. Firstly, we've got our local regional operational teams, and when they identify an ongoing risk from a reactive issue, they can add the area and the sewers onto the ongoing programme of regular planned sewer cleaning. These jobs are termed legacy planned sewer cleaning jobs, and the example in the map on the left shows a pollution cluster where the squares are on the watercourse, where the sewers highlighted in green have been added to the planned sewer cleaning programme. This year, we're delivering 2,000 kilometres of planned sewer cleaning across the whole of the operating area, and approximately 20% of the programme comes from the legacy jobs. The remaining 80% of our planned cleaning programme is made up of tactical jobs, which are jobs identified through the data-led targeting that we've built into the Icubed below ground risk model. The example map on the right shows historical blockage incidents from the last 3 years, which are the little brown circles on the map, converted into blockage hotspots overlaid on the sewers. The area inside the blue dashed circle has an intense blockage hotspot, which has contributed to high risk scores on the sewers in that area and selected those assets for the tactical cleaning programme. Next slide, please. I'm going to have a look now in a bit more detail at how these data-led rules work in the model and how we use them to target the tactical planned cleaning jobs. So the first step is to calculate a standardised escape of sewage score for every sewer asset in Thames Water. The escape of sewage score uses the last 3 years of sewer blockage, internal and external sewer flooding and pollution incidents, joins each incident to the nearby sewers, and then applies weighting for the recency, frequency and total number of incidents to calculate the overall escape of sewage score for each asset. Next, please. We then use high consequence data sets such as sensitive watercourses, serious pollution incidents and sites of special scientific interest and basement properties to increase the risk priority on assets that are related to those high consequence risks. Next, please. The sewers are ranked by risk priority to select the highest risk assets for the planned cleaning programme, but intersecting sewers with medium risk are also added into the programme so that we clean connected sewers that might be contributing to the blockage issues in an area. And the example in the map there shows the high risk red sewer and then the intersecting medium risks that have been joined on to create the overall job. Next, please. And the final list of sewers that we've selected for tactical cleaning are then grouped into individual jobs based on connected sewers, and delivery factors such as permitting requirements and the traffic sensitivity are added to the jobs, which helps with our planning and delivery teams for the end-to-end joined up process. Next, please, Anna. To improve the benefits that we achieve from these planned programmes, we're using data insight from incident root causes, asset characteristics and area characteristics to assign relevant interventions to different types of sewer failure. So interventions are also combined within the same sewer network area so that they complement each other. And the map on the right shows an example area where multiple different planned programmes are being delivered all alongside each other. In this area, we've got sewer blockages that were caused by fats, oils and grease, and multiple restaurants nearby. So these food service establishments, or FSEs, are shown on the map as little diamonds. Our network protection team visited each of these FSEs to discuss appropriate grease management practices. Sewers with high escape of sewage risk scores, highlighted in green on the map, they're automatically prioritised onto the planned cleaning programme to address repeat blockages. Then we have asset deterioration modelling, and we use that to identify sewers with potential structural condition defects. And these are highlighted in light blue. So those assets were put onto a structural CCTV survey inspection programme instead of sewer cleaning, and the survey results then feed into the subsequent sewer rehabilitation programme. Where the model identified blockages caused by persistent sewer abuse, so a root cause of fat, oil and grease, or paper and rag, then customer education was also targeted on the residential properties in the area, and the properties in the pink and blue shaded areas are where we've had the customer education. And then finally, the overall delivery timing of each intervention is planned to maximise the benefit. So we work with our delivery teams and the contractors to align when we do the sewer cleaning with when we do residential customer education and network protection visits, so that we can clean the sewers and then prevent material building up again in the cleaned network. Thanks for your time. I'll hand over to Alan now to introduce the above ground model.
Thank you, Chris. Morning, everyone. My name's Alan Jeffrey. I head up a team of analysts that support above ground assets within the operational side of Thames Water's waste network business. Next slide, please, Alan. A key principle we focus on is that alarm management is inherently reactive, whereas assessing behaviour change that result in alarms is predictive. This key behavioural insight is a core component of our Icubed tool. I'd like to show you some examples of how we exploit operational technology through the application of data science, some of our Icubed tools, namely behavioural heat mapping, performance benchmarking, and digital pump balancing. Next slide. The diagram on the left is something we can all relate to. It's a health check with your GP, measuring all the key parameters: heart rate, blood pressure, BMI, blood sugar, liver function, and so on. Based on the results, a number of conditions can be detected and advice can be considered about how to best extend or sustain the life of the asset. Regular or live sampling can be used to build a profile of insight on stability and stress and risk. We can then check changes in behaviour under different scenarios against previous iterations with known outcomes. And this is our benchmarking. The middle diagram shows how this can be applied to pumping stations, measuring those attributes that describe the operation of the process. Using the previous example, flow could be blood pressure, starts per hour would be pulse, blockages relate to BMI, blood sugar could be septicity, and so on. Behavioural change relates to stability, i.e. the ability to sustain repeatable performance under various scenarios. Changes in stability can be data enriched to accentuate key factors such as risk, performance, efficiency, and effectiveness. Behavioural change is a lead indicator and an enabler to dynamic diagnosis, appropriate intervention, symptom closure, and benefit tracking. From the data models used, we can diagnose a number of operating issues, many of which are listed here. The right-hand diagram shows how this is applied. In this simple example, we create a rolling 60-day behavioural footprint per site. This is its DNA, this is its benchmark. We then assess the last 7 days operation against the benchmark to reveal the key behavioural change. Basic RAG rules then apply to the results, where our immediate focus is on risk of failure, then performance opportunities. Next slide, Anna. This is a recent heat map used to visualise pumping station behavioural changes. It does it per department and distills the top 10 results by magnitude of change. The data is used to describe the operation of the assets in the process. It's arranged in logical groups showing the comparison of the previous to recent period, that being the 60 and 70 days respectively. Next. Here's a site where pump starts on average 162 times a day. That's for the last 60 days. And in the last 7, this has increased by 55%. That's quite a normal variant. Hourly starts, however, have increased from 7 to 12 per hour. Now, that's becoming more of a concern. Runtime, measured in minutes, is stable but lower. This implies repeated pump trips, more starts, less runtime. It appears that this site has something as a history, 22 alarms per day for the last 2 months. That's far from ideal, but note the average has now dropped to 6. But in the last week, it's peaked at 44 in one day. Now, events. These are the things that are intended to happen as normal operation, the heartbeat of the site. This has increased from 478 per day to 1,003 per day. This site seems to be in some form of shock. But it's an example showing that the lower level of detail, that's where the insight is hiding. It's not in the alarms. Next slide, please, Anna. Behind these statistics are the detail records. Multiple data streams collaborate to allow a logical and comprehensive view of the site operation per day, per asset, per data stream. Energy, pump starts per hour, per day, per asset. Alarm groups and event groups describe the operation of the day per dimension using the metadata. Heat mapping helps as a visual aid. Next. Immediately, we can see this has occurred on the 26th of April, and note pump 2 fails to operate. Next. Also note now that the repeated backup operation happens at the same time, implying a defective backup control or an ineffective pump. Next. Detail investigation reveals that insight was available nearly 3 days prior to this event. It's a further confirmation that the intelligence is resident in the basic operational data, and alarm behaviour is consequential. Next. The same data can be used to validate pump performance. This is especially effective in pump sets or families, or to give us what we call a sibling check, on the assumption that the flow in a pumping station does not vary significantly in any given hour, and where a station operates at more than 24 starts a day, data can be used to calculate the wet well cycle times and check the effectiveness of siblings to perform the same task against each other. This sample data shows a typical result set. You can see here that pump 1 is taking nearly twice as long as its sibling to perform exactly the same task. Pro rata these unit cost and basic consumption calculations, it shows that on a 10 kilowatt asset, continued imbalance, if it's left unchecked, would have cost an additional £700 a year. Next slide. Case studies that I'd like to go through show these tools in operation. Here's an example of a low flow site. Stats reveal that it usually operates less than 4 times a day and consumes about 1 kilowatt a day. The heat mapping tool targeted this site for 3 key reasons. Increase in energy from 2 to 37, increase in starts from 2 to 37, increase in energy from 1 kilowatt to 38, and increase in events by 1,000%. The wet well cycle profile shows that the site is in some form of anaphylactic shock, and alarms and wet well cycle profile suggest the backup control or NRV issue. Next slide. Attendance on site revealed that the pump was not seated or sealed correctly. The backup control here is operated by electrodes, and spray from the failed seal initiated the backup system, which is restricted to operating as if it was in both a full and empty state. Can you play the video, please, Anna? Thank you. Pump was reseated. Backup control check for correct operation, but data is used to confirm successful intervention, as you can see at the lower part of the slide. Validation of symptom closure is a key part of the process. Next slide, Anna. Case study 2 shows a 2-pump station operating at a duty standby regime. Energy benchmarking and pump balancing identify pump 2 as having performance issues. This is clearly demonstrated in the runtime comparison of the symptom graph. Pump 2 was lifted, blockage cleared, damaged impeller replaced. The resolve graph demonstrates how load was balanced across the pump set, and the reduced monitor running current confirms the closure of the symptom. Next slide. Tracking performance against each site's own benchmark and visualizing performance through heat maps are key tools. It brings about focus and enables performance to be quantified in OPEX terms, supporting our critical decision making and prioritization. This example would have cost an additional £1,200 a year if left undetected. Next slide. Case study 3 shows another 2-pump duty standby site. Energy benchmarking, changes in event and alarm behaviour, and erratic wet well cycling were the focus for this site. This is clearly demonstrated in the runtime comparison of the symptom graphs. The site triage identified non-return valves failing to operate correctly and were replaced. The resolve graphs demonstrate the symptom closure and the resultant stability of the operation of the site. Next slide. Symptom evaluation reveals an OPEX impact of just shy of £2,500 a year. It's another example of how tracking behavioural change against baseline on a site-by-site basis is a major contributor to predictive intervention. Our current developments on taking this further forward are around application of machine learning and artificial intelligence, and upsizing and developing the algorithms and models to apply this at a network, system or catchment level. Thank you for your time and attention. I hope you found this useful and informative. I'll pass you back to Anna in the studio.
Excellent. Thank you very much, Alan, and thank you very much, Chris. As Alan said, I hope you found that interesting. There was a lot to get through in a short space of time. I believe we've got kind of 3 or 4 minutes now for any questions.
Yes, we do, Anna, and I've got a couple here for you. And I would just say to everybody, please note the contact details on the screen there for Anna, Chris and Alan, which I'm sure all of them will be very happy to hear from you if you have any questions that are not able to be answered today. But the first question I have is, at what frequency do you operate this analysis?
Yeah, Chris, do on the network, and Alan can answer the pumping.
Thanks, Bob. For the below ground model, we've built it in a way that we can operate at different frequencies for different interventions, and that's driven partly by the delivery needs that we've got with our contractors. So for our planned cleaning programme, we run it every 6 months to build a large work pack of sewers that our contractors can then have time to plan in and deliver the work efficiently. Excuse me. For sewer depth monitors, we run the model every month, and we have a much more frequent view of the risk to pass across to our delivery teams. And we've actually developed another model called the virtual blockage alarm tool in the last couple of years, which is a fortnightly run of the model, where we look at underlying risk in the network, where we keep visiting areas and use that as a very frequent way of identifying risk and getting inspection teams out to try and identify problems that are underlying in the network.
Okay, thanks very much indeed for that. The next question I have for you is, can you describe the data platform used for this?
Do you want to have a go at that, Anna? Joking.
I'll leave that to my technical experts.
For sure, we've made quite a sizable investment in Microsoft's Azure stack across the organisation. So the kernel of it is Azure, which is deployed across the enterprise. We've built a number of data gateways which enable us to consume data into a common place. That's a SQL-based environment, a mix of data warehouses, analysis services, and provision into a data lake. We then build analytical data cubes in SQL. The results are then consumed by users through a mix of applications, which range from spreadsheets hosted on SharePoint, Power BI, Access, Power Apps, and for old time's sake, there's a few PowerPoint slide decks rolling for good measure.
Okay, thanks very much indeed. And I think we've got time for just one more now. Very quickly, what future developments are planned?
I'll briefly talk about that, and then I'll open it to Alan and Chris if you've got anything else to add. I think one thing that we're really, and this is an AMP kind of over the next 3 or 4 years, we embarked on a journey called Smart Waste, and that's been kind of the preparations for that have been ongoing for about 18 months. And the thinking and the kind of aspiration around Smart Waste is to have a truly intelligent catchment approach. So we're far better now at understanding what our pumping stations are doing and the risks associated to that. Equally on the network, we're getting more and more coverage on our network. Traditionally, we haven't got X-ray eyes, we can't kind of see what's going on underground, but with the implementation of things like sewer depth monitors, we are moving more into that space. And the smart network is taking those things, putting them together, and ultimately, hopefully, getting the treatment assets involved in that, so we can really have an understanding of what's going on in our catchment at any given time, and react accordingly, either on an operational basis, but certainly on a tactical and strategic view as well. I could spend all morning talking about smart waste. I know we're running out of time, and I'm sure that's something that we'll come back and talk about in the future, but longer term, smart waste is the way to go.
Thanks, Anna. If I can come in on that one, we are out of time now, so I'm going to have to bring the session to a close. Can I say to you, Anna, Alan and Chris, thank you very much indeed for the presentation, most enjoyable. And thank you also to everyone for attending. On the next slides, I'm going to show you details of the following sessions, and I do hope you'll take the opportunity to go along and visit those if you can. But otherwise, thanks very much indeed, everyone, and goodbye for now. Thank you.
Thanks, Bob. Thanks all.
Thank you.
Thank you. Thank you.